Ever wonder how a robot could follow a command like, find the rabbit's favorite vegetable and place it on the plate, without being told exactly where to look or what the vegetable even is? That's the magic of vision language action, VLA, models, AI systems that blend seeing, understanding, and doing. But here's the real question. Can they handle the messy, unpredictable world we live in? Let's dive into a study that's shaking up how we test these smart robots. Traditional robot tests are like training wheels. They're great for basics, but not for real-world chaos. They're either too simple, like put A on B, or too narrow, focusing on one specific task. But the real world, it's full of surprises, weird objects, confusing instructions, and distractions. So researchers built something new, INT-ACT, a simulation-based benchmark with 50 tasks across 10 categories. Think of it as a robot's ultimate obstacle course. Let's break down what INT-ACT tests. First, object diversity. Can the model handle items it's never seen before, like a screwdriver or a toy car? Then language complexity. Does it get confused by tricky phrases like, put the rabbit's favorite vegetable on the plate, versus a straightforward, put the carrot on the plate? And finally, vision language thinking. Can it ignore distractions, like spotting a spoon in a pile of clutter? Here's the twist. Even though VLAs are great at understanding tasks, their intentions are solid. They often stumble when it comes to executing them. Imagine a chef who knows the recipe, but can't chop the vegetables properly. For example, a model might perfectly parse, put the nut on the wheel, but fail if the wheel is oddly shaped or the nut is hidden under a towel. And here's a surprise. Fine-tuning these models on specific tasks can actually make them worse. It's like teaching a student to memorize answers for one test, but failing when faced with a new question. So why does this matter? VLAs are supposed to be the future of robotics, flexible, adaptable, and ready for anything. But without benchmarks like INT-ACT, we're flying blind. By open sourcing their tasks and code, the researchers are giving the whole community a tool to bridge the gap between understanding and doing. Now let's shift focus to the latest breakthroughs. Imagine teaching a robot to tie your shoes without writing a single line of code. That's the magic of visual instruction tuning, a 2023 breakthrough where AI learns by watching videos or images. But here's the twist. It's not just about seeing, it's about understanding the why behind the task. Like if you say, put the carrot on the plate, how does the robot know it's not supposed to drop it on the towel? That's the puzzle researchers are solving with spatial reasoning, a fancy way of saying, how does the robot see the world and figure out what to do? Enter SpatialVLA, a 2025 study redefining how AI connects vision, language, and action. Think of it as a robot's brain that's learning to map objects in space, like a mental GPS. The team trained their model on a dataset called Bridge V2, which simulates real-world tasks. Think picking up a mug, sorting objects, or even navigating a cluttered kitchen. But here's the clever part. They didn't just let the model memorize steps. They tweaked its thinking process, like adjusting how it weighs details, e.g., the exact size of an object versus padding with generic data. And guess what? That tiny change made a big difference in performance. Now let's compare it to other models. When tested on tasks like put the carrot on the plate or avoid the towel, some models struggled. Take Polygemma, it'd repeat instructions instead of adapting. But others, like SpatialVLA, showed promise. Yet even the best models hit roadblocks. For example, SpatialVLA had trouble with a Coke can on a plate, while Magma, a different model, handled it better. Why? Because real-world tasks are messy. A robot might know what a carrot is, but it still needs to figure out where it belongs. Here is where language gets tricky. Abstract instructions, like don't put the carrot on the plate or find the red spoon, stump even smart models. They'll follow the words but miss the nuance. And then there's the common sense gap. Why would a robot know a spoon doesn't go on a towel? It's like teaching a kid to ride a bike without explaining gravity. But here's the good news. Researchers are getting closer. The best models combine fine-tuning, adjusting their internal settings, with rephrasing strategies, helping them reinterpret instructions. It's not perfect yet, but it's a step toward robots that can handle the chaos of real life. So what does this mean for the future? Imagine a robot that can not only follow your commands, but also adapt when things go sideways. Whether it's a messy kitchen or a crowded street, this research is paving the way for AI that's truly versatile. The next time you see a robot on a factory floor, remember, the real challenge isn't just making it follow instructions. It's making sure it can handle the unexpected. And that's exactly what INT-ACT and SpatialVLA are helping us tackle. Thanks for watching. If you want to explore how these models work in action, check the links below. And hit subscribe for more deep dives into the future of AI. Until next time, stay curious, and let's keep pushing the boundaries of what robots can do. Rock it!